Okay, so more M-dwarfs. I guess you are loving M-dwarfs by now, and you know a lot about them. So I was going to talk about what they are, but I don't think I should do that now. You know that these are very small stars, low luminosity stars, and we are very much interested on them. So the problem with M-stars is their activity. What we know is that most M-stars, what you are seeing here is the mass of the stars, here is the sun, and here is a proxy of the activity of the star. This activity is in the atmosphere of the star, and it's basically measured by the ratio of the luminosity of the X-rays over the luminosity, the total luminosity of the star. So what you can see here, as we go to lower mass, lower stellar mass, you can have higher and higher X-ray luminosity compared to the total luminosity of the star. So this means that these stars, these low mass stars, are highly active, and especially we have this one, AD Leo. This line here shows you the difference between the usual AD Leo during a quiescent state and during a flare. This is the difference between a flare. It's 1 order of magnitude difference in the X-rays. So basically, one of the features of activity is the flares. This is, of course, not a flare from an M-dwarf because we cannot take a photograph of that. This is a flare from the sun. But this is a measurement of a flare, a big flare from AD Leo that was measured in 1986. So what you are seeing here is the flare in different light. This is UV, this is the blue light, this is yellow light, this is red light. And you can see how this zero doesn't mean that there is no light at all. It means that this is quiescence. So this thing goes up and then down. So basically this is the only flare we have measured in the UV and in the optical. So why we need this? Because in order to feed up our models, or photochemical and climate models for simulate atmospheres of planets, we need to have the optical part of the spectrum and the UV part of the spectrum. The UV controls the photochemistry, and the optical part and the red part of the spectrum controls the temperature of the planet. So it's very important to have both of them. So this is a large flare with a lot of energy, and it lasted for 4 hours, but we are going just to take the first 20 minutes of the flare, which is where most of the energy was developed. So oxygen, as Vicky already told you, is a very, very nice feature as a biosignature. We like it a lot. And basically what I'm going to show you here, it's a spectrum of 3 planets. The green one is present Earth, and you can see the oxygen over there. This is the absorption of oxygen. And then you can see here 2 planets that are Earth-like, early Earth-like planets. If you like to believe that there was high amounts of oxygen, of CO2 back then this would be the Archean Earth. If not, it's just a planet-like Earth. So basically, this red and this blue one are the early Earth, or something like that, with high CO2, but no oxygen over there. There was no oxygen back then. The oxygen there was, as I'm going to show you, it was just a very few. And then we have this byproduct of the oxygen, which is the ozone, which is here, which is detectable in the infrared. So if we want to have infrared detectors, we can have the ozone, which is seen here in the green. Again, this is the present Earth. But if you go to high CO2 atmospheres, then it gets swamped under the absorption of CO2. So these are, again, 2 cases for a kind of early Earth. And you can see here, these 2 absorption lines are CO2. So basically, you wouldn't see ozone even if it's there. And this was pointed out some time ago by Frank Celsis and collaborators. So this is our flare. This is the way we measure the flare. And this is how our model sees that flare. So basically what you have here is the first is the quiescent star. This dotted line is the sun. It's what the Earth receives from the sun, the flux that Earth receives from the sun. And this is the flux of the star as the flare develops and goes on and then down. So this is back to quiescence. So we put that on two models, a photochemical model and a climate model. It's basically to do two kinds of planets. One is the present Earth-like planet, basically 21% of oxygen. And then these Earth-like planets where we have 20% of CO2, 1 bar surface pressure. And we use two methane mixing ratios just because we are not sure how much methane we would have in the past. So we just took these two just to test what would happen. So I'm going to show you the results for the flare with high oxygen. So basically, during the flare, you see here the ozone number density. And during the flare, you see there is this depletion in the stratosphere. And then it goes back to the initial steady state. And here I show you the fraction of the change of the ozone column dip. And you can see it's just a few, it's just 1%. So it's very, very few, it's just a small change in the whole ozone column dip. So basically the flare doesn't do that much to the ozone in this high oxygen planet. So what happened in the surface, what you are seeing here, this is the flux in quiescence at the top of the atmosphere. This is the top of the atmosphere flux at the peak of the flare. And then these lines, the continuous lines, are the flux at the surface of the planet. So this is the UV. All biologists and all the people that use this sunscreen cream know that this is dangerous. This is less dangerous than this one, and this is a little bit dangerous. So basically what you are seeing here in the dotted line, again, is the flux, the UV flux that comes into the surface of Earth around the sun. So basically what you can see here, even in the flare, during the peak of the flare, you get just a little bit more UV radiation than you would have in Earth's surface. So basically you are very well protected there. But then what happens if you have your flare with a proton event? The proton event is when you have these high energy charged particles coming out of the atmosphere. So what happens there is that these protons create a chain of chemistry that basically produces NO. And this NO destroys ozone. So what we are thinking here is that the planet has no protection, has not a magnetic field protection, because if the planet has a magnetic field, then you don't need to do this calculation, because simply these protons are going to get into the poles, the magnetic poles, or are going to go away. So what you see here is that there is really a change in the ozone layer. You can see here how the ozone layer is depleted as the flare goes on with the protons, including this. But the thing is, when you see the surface flux again, here is the UV surface flux. You can see that there is just a small amount of time here when you exceed the UV that you receive on Earth. So I'm going to go now, so basically you are safe here. So I'm going to go now to the high CO2 atmosphere, and I want you to notice these things. So this is the atmospheric composition on a steady state on a 20% CO2 atmosphere. So this is the amount of oxygen you are going to have, and this is the amount of ozone. And I want you to notice the present ozone and the ozone here. So this is oxygen that comes out of the photolysis of CO2. And you can see here, CO, a lot of food for microbes, and this oxygen here. So there is two things to explain here. One is why there is so much ozone here, and this is something that was noticed by Sean Goldman before and Picky Meadows. I don't think it's published, but they noticed it first. And why is there so much ozone, and then why there are so many oxygen compared with the same planet but under the sun. So I'm going to try to explain this quickly in 1.5 minutes, both things. So it happens, this is the quiescent spectra from 80 Leo, and this is the sun spectra at 1 AU. So this is what the habitable planet receives around 80 Leo, and this is what a habitable planet receives around the sun. So why there is so many ozone? It is because here you are destroying, here in this planet, you are destroying more oxygen, and then you create ozone, because when you destroy oxygen, you create ozone. So that's why there are so much ozone, because then the ozone doesn't get destroyed here, you see, because there are less photons here to destroy the ozone. Now, why is there so much oxygen? Well, this has to be with water. See here, this is oxygen in these atmospheres, and this is oxygen in the same atmosphere but around the sun. And what you can see here is that the difference is in the lower part of the atmosphere, in the troposphere. And the reason for that is because you have water photolysis right here, and in this planet around the sun, you have a lot of water photolysis that creates H and OH, and that destroys the oxygen. But then in these planets, you have less photons there, so you don't have that much H and OH, and then you can build up this amount of oxygen. So I hope I explained that correctly for you. And see, this is very nice. This is the flare. This is the UV flux in the surface during the flare. So basically, you have these two planets that are more protected than the same planet with the same CO2 amount during the same flare. So this is not under a flare, around the sun. So this is the flux in the surface for a planet around the sun with 20% CO2, and this is the surface flux of UV that you are receiving in this planet around an active M-stars. So you are actually better there. So those are my key points. I'm going to stop there. You can read the conclusions, because I'm sure you read English better than I do, and I will accept questions there.